everyone, welcome to our channel Knowledge of. Friends, subscribe to our channel and click the bell icon for the latest update. आज हम लोग जो क्लास करने वाले हैं वो क्लास हम केमिस्ट्री की क्लास करेंगे। केमिस्ट्री की क्लास की अगर हम बात करते हैं तो हम 143rd क्लास करेंगे। ऑलरेडी हमने 142th क्लासेस कर लिया है। एंड फर्स्ट ऑफ ऑल अगर हम इसकी बात करते हैं तो हम आज जो डिस्कस भी कर रहे हैं वो थर्मोडायनेमिक्स कर रहे हैं। इससे पहले ऑलरेडी हमने स्टेट्स ऑफ मैटर इन चैप्टर 1, चैप्टर 2, यूनिट 1, यूनिट 2, यूनिट 3 ऑलरेडी डिस्कस कर लिया है। ओके तो थर्मोडायनेमिक्स हम स्टार्ट कर रहे हैं, जो कि अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, इट्स अ ह्यूज रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुँचे। एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो सो दैट ज़्यादा से ज़्यादा लोग के पास वीडियो पहुँचे और ज़्यादा से ज़्यादा लोग इसका यूटिलाइजेशन भी कर सकें। Now we are talking about the thermodynamics. So in the thermodynamics we start today's topic, that is your measurements of an delta U and a delta H with in terms of calorimetry. कैलोरीमेट्री प्रोसेस के थ्रू हम करेंगे, जिसमें हम मेजरमेंट्स करेंगे डेल्टा यू और डेल्टा एच का विद यूजिंग द कैलोरीमीटर. ओके so in terms of the calorimeter, measurements of the delta U and the delta H with reference to the calorimetry, we can measure energy changes that is associated with the chemical or the physical processes by an experiment technique that we can say that that experiment is known as calorimetry here. Okay, in the calorimetry, the process is carried out in the vessels. एक vessel में carried out होता है calorimetry में process, and the process is carried out into the vessels that is called calorimeter. और जिस vessels में वो यूज होता है हम उसे कैलोरीमीटर बोलते हैं. ओके एंड विच इज इमर्स्ड इज नोन एज द वॉल्यूम ऑफ लिक्विड. और जिसके अंदर वो इमर्ज होता है, एक्चुअली मैं यहाँ पे डायग्राम आपको बताऊंगी, तो जिसमें इमर्ज होता है वो वॉल्यूम ऑफ दैट पर्टिकुलर लिक्विड होता है. नोइंग द हीट कैपेसिटी ऑफ द लिक्विड, अगर हम बात करें कि रेफरेंस टू द हीट कैपेसिटी ऑफ अ लिक्विड हियर, so where that it will be, that particular liquid, that knowing the heat capacity of that liquid, where that heat capacity of that liquid in which the calorimeter is immersed, and the heat capacity heat capacity of that calorimeter with reference to that, it is possible to determine the heat that is evolved in the process by measuring the temperature changes, where the measurements are made under the two different condition. जो measurements है वो आपके दो different conditions के basis पे होती है. फर्स्ट है आपका at constant volume, एक constant volume पे, जो से हम QV से denote करते हैं, which is represented by a constant volume. The second will be the at constant pressure that is represented by the QP here. Okay, so this is the two measurements that are made under the different conditions, that is at the constant volume as well as at the constant pressure, reference to the measurements of the delta U and the delta H calorimetry. Now with reference to that, we will discuss the first one, that is delta U measurement, that what we have to discuss here. In reference to the delta U measurements here for the chemical reaction, so here the delta U measurements states that for a chemical reaction, heat absorbed at a constant volume is measured in a bomb calorimeter, and where we are dealing with the constant volume in reference to that is measured in the bomb calorimeter. This is a figure here, and this is a vessel here that is filled with water here, and this is your bomb, and then after that this is a sample here. Okay, this is an oxygen inlet, and this is a steamer, this is a thermometer, and this is your stringlets here. Okay, this is the stringlets, and this is under this bomb, that is oxygen under the pressure is filled here. Okay, this is a whole figure that is of bomb calorimeter. In reference to the figure here, where as you can see that a steel vessel, a steel vessel, that is the bomb, is immersed in the water bath. Okay, the whole device is called as in the form of the calorimeter. ये पूरा device जो है वो हम उसे हम कहते हैं calorimeter. With reference to the calorimeter, the steel vessel is immersed in the water, as you can see that the bath, to ensure that no heat is lost to the surrounding. A combustible substance is to burn in a pure dioxygen supplied in the steel bomb, and that heat evolved during the reaction is transferred to the water around the bomb, and its temperature is monitored. Since the bomb calorimeter is scaled, and that is by the thermometer, and its volume does not change, that is the reason the energy changes associated with the reactions are measured at a constant volume. Under these condition, if I'm talking about with reference to the delta U measurements, under these condition we can say that where that work is not done as the reaction is carried out at a constant volume. जब constant volume पे ये reactions ली जाती हैं at a constant volume पे, तो फिर क्या होता है कि आपका कोई भी work done नहीं होता. With reference to the bomb calorimeter, even for the reaction that involving gases also, there is no work done has been taken, that is of delta V is equals to 0. अगर हम reference to the gases की बात भी करते हैं तो उसमें भी कोई work done नहीं होता. Temperature changes of the calorimeter produced by the completed reaction is then converted into, that is of Q of V, by using the known heat capacity of that calorimeter. Okay, that is what the experiment has been done about. Now we are dealing with the delta H measurements here, and that is delta H measurements क्या होते हैं. In reference to the measurement of delta H measurements, while we are dealing with the delta H measurements here, in reference to that, measurements of heat changes at a constant pressure, that generally under atmospheric pressure, that can be done in the calorimeter. Okay, and that we'll discuss in the figure also. We know that the delta H will equals to the QP, that at constant pressure, and therefore heat absorbed or evolved, that is of by QP here, and that at a constant pressure is also called the heat of the reaction, or हम इसे heat of reaction भी बोलते हैं, या फिर हम enthalpy ऑफ रिएक्शन बोलते हैं. ओके, तो एंथैल्पी ऑफ रिएक्शन जैसे हम डेल्टा एफ ऑफ एच, आई ऑफ एच बोलते हैं. अगर हम एक्सोथर्मिक के केस की बात करते हैं इन द टर्म्स ऑफ, इफ हम टॉकिंग अबाउट द एक्सोथर्मिक कंडीशन डेल्टा एच मेजरमेंट्स के रेफरेंस में, सो वेयर इन एन एक्सोथर्मिक रिएक्शन हीट इज इवॉल्व. एक्सोथर्मिक में क्या होता है, हीट इवॉल्व होती है. एक्सोथर्मिक का मतलब होता है हीट बाहर आती है. ओके, एंड द सिस्टम लूजेस हीट टू इट्स सराउंडिंग, और जो सिस्टम होता है वो अपना हीट को आउटवर्ड भेजता है, सराउंडिंग में भेजता है. Therefore, QP will be negative. QP उस टाइम पे नेगेटिव होता है because delta R of H will always be negative, क्योंकि delta R of H जो होगा वो हमेशा नेगेटिव ही निकलता है. Similarly in the endothermic reaction, जब endothermic reaction होती है जो कि heat absorbed होती है, heat is absorbed, that is of QP is positive and that delta H will be the positive. तो क्योंकि अगर एक्सोथर्मिक रिएक्शन है तो इस चीज़ को बिल्कुल दिमाग में बैठा लो कि अगर एक्सोथर्मिक रिएक्शन है तो जो QP है वो भी नेगेटिव हो गया, तो डेल्टा RH की वैल्यू जो है वो भी आपकी नेगेटिव होगी अगर एक्सोथर्मिक रिएक्शन है. अगर एंडोथर्मिक रिएक्शन है तो QP भी आपका पॉजिटिव होता है, और आपका डेल्टा RH भी जो होता है वो भी आपका जो होगा वो पॉजिटिव ही होगा. दैट यू हैव टू अंडरस्टूड, क्योंकि इसमें तो समझने में तो आप ऑलरेडी समझ लोगे, बट इन द केस ऑफ द न्यूमेरिकल अगर उन्होंने बोल दिया एक्सोथर्मिक रिएक्शन है या एंडोथर्मिक रिएक्शन है, या फिर रिएक्शन को देख के आप समझ गए कि ये एंडोथर्मिक है कि एक्सोथर्मिक है, उसके अकॉर्डिंग आपको आसानी से पता चल जाएगा कि जो इसकी वैल्यूज आएंगी, जो QPs इसकी वैल्यूज आएंगे, या जो इसकी डेल्टा RH वैल्यूज आएंगी वो पॉजिटिव होंगी कि नेगेटिव होंगे. तो उससे आपका वो थोड़ा कॉन्सेप्ट क्लियर रहेगा, क्योंकि पॉजिटिव और नेगेटिव वैल्यू बहुत फर्क करता है. ऐसा नहीं कि 1.08 किसी का आंसर है तो प्लस में आ रहा है और आपने माइनस 1.08 कर दिया तो बहुत ज़्यादा डिफरेंस बन जाता है. तो इसलिए इस चीज़ का थोड़ा ध्यान देना पड़ेगा कि एक्सोथर्मिक रिएक्शन है तो QP नेगेटिव होता है, हीट इवॉल्व होती है, एज वेल एज जो डेल्टा RH होता है वो भी आपका नेगेटिव होता है. एज वेल एज अगर इन द केस ऑफ एंडोथर्मिक रिएक्शन में क्या होता है, हीट जो एब्जॉर्ब होती है, QP जो है वो पॉजिटिव होता है, डेल्टा RH भी जो होता है वो आपका ऑब्वियस बात है पॉजिटिव होता है. Now moving ahead with the diagram and with the numerical that we have to discuss here is, this is a diagram that we will discuss in the delta H measurements here. This is a bucket type structure, and this is a thermometer. Okay, this is a thermometer hole that is inserted in it, and this is the formed polystyrene cup है polystyrene की, और as well as ये जो है थोड़ा सा अंदर का शो कर रहे हैं, क्योंकि अब वैसे आते कप के अंदर का कैसे शो करेंगे. ये रिएक्शंस जो मिक्सचर्स हैं वो इसके अंदर है, ऑलरेडी यहाँ पे थर्मोमीटर उसका टेम्परेचर चेक करेगा. This is what the calorimeter for measuring the heat changes at a constant pressure, and that is atmospheric pressure that they are checking here. With reference to that delta H measurement here, we will solve a question here. With reference to that, you have to be remember what I had told you in the before, that exothermic and endothermic. Exothermic reaction है delta आपका QP जो होगा वो आपका नेगेटिव होगा, एंड एज वेल एज डेल्टा H भी जो होगा वो नेगेटिव होगा. एंडोथर्मिक रिएक्शन है तो आपका QP जो है वो भी पॉजिटिव होगा, और डेल्टा H भी जो होगा वो पॉजिटिव ही होगा. Now moving ahead with a question here, and that is of your question, 1 gram of graphite is burnt in a bomb calorimeter. 1 ग्राम आपका ग्रेफाइट जो है वो अगर बर्न किया जाता है बॉम्ब कैलोरीमीटर में इन एक्सेस ऑफ ऑक्सीजन ऑफ 298 केल्विन, आपका जहाँ पे एक्सेस जो होती है अगर 298 केल्विन एक्सेस है एट 1 एटमॉस्फेरिक प्रेशर according to the equation here. Okay, here we have a C. C is in the form of graphite and plus O2 that is in the form of gas, and the CO2 that is in the form of the gas here. As well, during the reaction, the temperature rises from 298 Kelvin to 299 Kelvin here, जो कि reaction जब हो रही होती है तो temperature जो है वो 298 Kelvin से लेके 299 Kelvin में rise हो जाता है. If the heat capacity of the bomb calorimeter is 20.7 Kelvin joule per Kelvin, and that is what is the enthalpy change for the above reaction at 298 Kelvin at 1 atm. आपको बताना है कि क्या एंथैल्पी चेंज आपको देखने को मिला जब 298 केल्विन 1 atm प्रेशर पे था. Now with the solution of this particular question here is, suppose Q is the quantity of heat. Q को अगर हम quantity of heat suppose करते हैं from the reaction mixture, that is of CO as C of V is the heat capacity of the calorimeter, then the quantity of the heat absorbed by the calorimeter is Q equals to C of V into that is delta change in T. This will be the heat absorbed by the calorimeter when we are finding out the quantity of that particular calorimeter. Now moving ahead here, where in that quantity of heat from the reaction will have the same magnitude but the opposite sign, because that the next last by the system, the reaction mixture is equals to the next that is gained by the calorimeter. If I'm talking about Q equals to minus C of V in delta T, that will put the value here, that is we have given this minus 20.7 kilojoule per Kelvin here, and that is multiplied by 299 minus 298 क्योंकि change हुआ 299 minus 298 Kelvin here. 299 minus 298 we will get 1 Kelvin here, and that is minus 20.7 kilojoule multiplied by 1 Kelvin. That will be the right answer as well. We'll get 20.7 kilojoule. As I told you कि जो Q होगा वो आपका तभी negative होगा when the equation will be the exothermic here. ओके, सो एक्सोथर्मिक अगर ये हमारे पास क्यों हमारा नेगेटिव आया है, सो ऑफ कोर्स जो डेल्टा एच निकालेंगे वो भी श्योरली नेगेटिव ही आएगा बिकॉज दिस इज एन एक्सोथर्मिक रिएक्शन हियर. नेगेटिव साइन इंडिकेट, ये जो नेगेटिव साइन है वो इंडिकेट कर रहा है कि ये एक्सोथर्मिक नेचर ऑफ रिएक्शन है, जैसे कि मैंने आपको बताया भी था. एंड दस डेल्टा यू फॉर द कंबशन ऑफ द 1 ग्राम ऑफ ग्रेफाइट इज इक्वल्स टू माइनस 20.7 किलो जूल इनवर्स. And for the combustion of the 1 mole of graphite, अगर हम combustion 1 mole of graphite की बात करते हैं, that is 12.0 gram a mole inverse multiply minus 20.7 kilojoule upon that is of 1 gram here. Then we solve this and then we'll get minus 2.48 into 10 to the power 2 kilojoule mole inverse, since delta n of G equals to 0 where delta H equals to delta U, and that is equals to minus 2.48 into 10 to the power 2 kilojoule mole inverse. This will be the, as you can see that as I told you कि अगर आपका Q negative है, that means the delta H will be also be negative, and this is the representation that the equation will be the exothermic here. Okay, exothermic reaction, that's the reason why it is negative here both sides. With reference to that, we have a next topic here that we have to discuss is enthalpy change. Enthalpy change, that is of delta R of H of a reaction, that is you can say that the reaction enthalpy. In the terms of the reaction enthalpy, in a chemical reaction, reactants are converted into the products and is represented by, basically जो reactants होते हैं that are converted into the product, and that is represented by the reactant and the arrow and that product here. The enthalpy change accompanying a reaction, that is called the reaction enthalpy. जो आपका enthalpy change आपके reaction में होता है वो उसे हम reaction enthalpy बोलते हैं. The enthalpy change of a chemical reaction is given by the symbol that is of enthalpy change, that is delta R of H, that is enthalpy change representing here. डेल्टा आर एच हम जो किस तरह से निकालते हैं, दैट इज ऑफ डेल्टा आर एच इक्वल्स टू सम ऑफ द एंथैल्पीज ऑफ द प्रोडक्ट, जितना भी प्रोडक्ट में एंथैल्पीज होती है उनको सम करोगे, देन माइनस सम ऑफ द एंथैल्पीज ऑफ द रिएक्टेंट. आप सम ऑफ द ऑल द एंथैल्पीज इन द प्रोडक्ट and minus sum of the all the enthalpies of the reactant, and then you can find it out delta RH, that is the reaction enthalpy. Now moving ahead, we will be having a short form of this to learn this with in the form of the, this is representing the sum of the, we'll use the sigma there that we have to discuss here, and with reference to that we will discuss the questions as well. Here you can see that delta R of H equals to, that I had told you, sigma I AI H, that is of product, and minus delta sigma I, and that is B of I H, and that is of reactants here. So this is the reaction. Here we have an equation, but before that you have to know one about thing, that here the symbol sigma that is represented here, that sigma is used for the summation, and this AI is, this was the sigma that is for the summation. Sigma, I will just write it down here. This is for the summation here, and that is of AI, and the BI, that AI and here is BI. These were the two that are your stoichiometry, that is a stoichiometric coefficient here, that are stoichiometric coefficient of the product and the reactant respectively in the balanced chemical equation. So for example, we take a equation here that is of CH4, that is in the form of the gas, and plus that is 2O2, and that is in the form of the gas as well, and that gives the product that is CO2 that combined with it gas and form, and then H2O that it forms, and in the form of the liquid here, and that is in the form of the gases. These were the two reactants about the gases here only. Okay, and so we'll just find it out, the delta RH, that is in the enthalpy reaction enthalpy here, change in enthalpy reaction, that is delta R of H equals to sigma of I AI and H of product, and sigma I BI H, that is of reactant here. These were the coefficient, stoichiometric coefficient, and this is the sigma that is representing the summation here. So how do you define this? As if sigma I AI H of product, that means that is H of M, and that is CO2, that we have a product here, CO2, and plus this is 2H2O, so we have an H2O here, 2 representing the sign of this, then minus, then HFM, that is CH4 here, that is CH4 plus, and that is plus 2, that is representing here, and that is O2 here in the form of the gases. Where HM, ये जो HM यहाँ पे आपको देख रहे हो, एक ये है और एक ये है, ये दो HM है, they are the molar enthalpies. What they are called as molar enthalpies. Okay, they are representing the molar enthalpies here. We are talking about enthalpies. The enthalpy change is a very useful quantity. That knowledge of these quantities is required when one needs to plan the heating or cooling required to maintain an industrial chemical reaction at a constant temperature. It is also required to calculate the temperature dependence of the equilibrium constant, as well as, if I'm talking about in terms of the first part, that is representing the enthalpy change, that is of delta RH, and the delta mu here, reaction of the reaction enthalpy, that refers to as your standard enthalpy of reaction. In the terms of the standard enthalpy of the reaction, that enthalpy of that reaction depends on the continuous under which a reaction is carried out. It is therefore necessary that we must specify some standards condition, and those standard condition, we can say that the standard enthalpy of a reaction in an enthalpy of the reaction is the enthalpy change for reaction. जो enthalpy change होता है reaction में, when all the participating substance are in their standard states. जब आपके reaction हो रहा होता है, तो आपका सारे जितने भी participate आपके substances होते हैं, वो सारे के standard states में होते हैं, तो वो आपका standard enthalpy for that particular reaction होता है. In terms of that, the standard state of the substance at a specified temperature is its pure form or at the rate of 1 bar. जो standard state होता है कोई substance का, वो आपका specified temperature पे ही होगा with a pure form, and that is of with reference to the 1 bar only. And here with reference to this, we have for example that the standard state of a liquid, अगर हम liquid ethanol की बात करते हैं, अब standard state की बात करिए तो फिर we'll take it liquid ethanol के केस की अगर हम बात करते हैं, that at 298 Kelvin is pure liquid ethanol. 298 Kelvin पे ये liquid ethanol जो होता है वो pure state पे ही होता है. Okay, pure liquid ethanol at 1 bar, and as well as the pressure is 1 bar. स्टैंडर्ड स्टेट ऑफ द सॉलिड आयरन, अगर अब हम सॉलिड आयरन की बात करते हैं, स्टैंडर्ड स्टेट की बात कर रहे हैं, तो solid iron that is at the rate of 500 Kelvin as pure iron at 1 bar pressure. Usually the data are to be taken as 298 Kelvin as well. Standard condition are denoted by the addition of the superscript. Basically हम जो standard conditions को denote करते हैं वो हम superscript जो कि हमारा denotation आपने देखा होगा इस तरह से होता है. Okay, and here we can represent to the symbol that is of delta h की representation में आपने ज़्यादातर देखा होगा, अभी तक का जितना आपने पढ़ा है उस हिसाब से delta h और आपने ऐसे सबस्क्रिप्ट देखा होगा. Okay, now moving ahead here. Now we'll discuss this B part, that is enthalpy change during the phase transformation. As you had understood about the standard enthalpy of reaction where we had discussed about the iron, solid iron and liquid ethanol as well. And enthalpy changes during the phase transformation because that is H2O that is in the form of solid and H2O that is in the form of liquid. Solid H2O से आपका liquid में change जो होता है that is of delta, that change in fusion, that is the subscript you can see here. 6.00 into that is 6.00 kilojoule mole inverse here. The delta of fusion of H abstract is enthalpy of the fusion in the standard state. अगर हम बात करते हैं standard state of enthalpy है fusion का, solid H2O और solid liquid आपका solid H2O और liquid H2O में आइस अगर आपका है, आइस से आप वाटर में करते हैं एंड देन ऑफ कोर्स यू आल्सो नो कि आपका अगर हो जाएगा तो ऑब्वियसली बात है आपको हीट करना पड़ेगा. The enthalpy change that accomplishing melting of 1 mole of a solid substance in a standard state is called standard enthalpy of the fusion or the molar enthalpy of that particular fusion here. अगर आप 1 मोल ऑफ कोई सॉलिड सब्सटेंस है उसको आपको मेल्ट करना है आपका स्टैंडर्ड स्टेट में अगर वो है तो उससे हम स्टैंडर्ड एंथैल्पी ऑफ फ्यूजन बोलते हैं, और या फिर कह सकते हैं आप मोलर एंथैल्पी ऑफ फ्यूजन भी बोलते हैं. दैट इज रिप्रेजेंटेड बाय द डेल्टा फ्यूज एज ऑफ सबस्क्रिप्ट हियर. H2O लिक्विड में है, अब यहाँ पे थे सॉलिड में था, लिक्विड में ट्रांसफर हो गया, अब लिक्विड में है एंड विद रेफरेंस टू दैट और लिक्विड से यू नो दैट हैज गॉन टू द gases here in the form. Okay, where in the form of the this equation that is comes to the solid to the liquid here, and that is the phase transformation also involves the energy changes, that is ice for example require heat for melting. Normally this melting takes at the constant pressure at that atmospheric pressure, and that is during the phase change the temperature remains the constant at 273 Kelvin here. Okay, with reference to this equation, when we are going to a H2O solid to the H2O liquid here, that is the fusion that has been taking place. So here the delta of a fusion, that is the enthalpy of the fusion, that is the standard state. If water freezes, अगर water freezes हो रहा है, freeze हो रहा है, and that then a process is reversed, तब आपका process जो होता है वो reverse हो जाता है, equal amount of heat is given off to the surrounding. And as well as reference to the enthalpy change that what we had discussed here in the terms of melting of the solid. अगर हम solid को melt करते हैं in the end that is endothermic, so all the enthalpies of the fusion are positive. Water requires heat for the evaporation at a constant temperature of its boiling point, that is represented by the TB here, and at a constant pressure as well. And if I'm talking about the H2O, that is in the form of the liquid here, and that is representing the H2O in the form of the gases here. And then when a liquid from gases, it vapors a position, that change in the vapors, that is of H substrate here, that is plus 40.79 kilojoule inverse here. This delta of vapor that has been represented here is the standard enthalpy of the vaporization here in terms of the vaporization. This is the standard enthalpy of the vaporization. Now moving ahead with reference to this only. Here in terms of amount of heat that is required to vaporize 1 mole of liquid at a constant temperature and under the standard pressure, that is a 1 bar, that is called standard enthalpy of the vaporization or the molar enthalpy of the vaporization, that is represented by the delta vapor H subscript here. तो जितना भी अमाउंट ऑफ हीट हमें रिक्वायर्ड होती है वेपोराइज करने के लिए, जो 1 मोल ऑफ लिक्विड आपका होता है, 1 मोल ऑफ लिक्विड को अगर आप कांस्टेंट टेम्परेचर पे और अंडर द स्टैंडर्ड प्रेशर 1 बार पे आप रखते हो तो हम उसे स्टैंडर्ड एंथैल्पी ऑफ वेपोराइजेशन बोलते हैं। और मोल एंथैल्पी जो वेपोराइजेशन की होती है दैट इज रिप्रेजेंटेड बाय द डेल्टा वेपर एंड दैट इज ऑफ एच सबस्क्रिप्ट हियर। इन द टर्म्स ऑफ द सब्लिमेशन अगर हम बात करते हैं तो सब्लिमेशन इज डायरेक्ट कन्वर्जन ऑफ सॉलिड इनटू द इट्स वेपर। सॉलिड से आप डायरेक्टली वेपर्स में जो कन्वर्ट करते हो फ्रॉम सॉलिड टू डायरेक्ट द वेपर्स फॉर्म, दैट इज नोन एज द प्रोसेस दैट इज नोन एज सब्लिमेशन हियर। सॉलिड CO2 जो होता है दैट इज अ ड्राई आइस जिसे हम कहते हैं, सॉलिड CO2 को हम ड्राई आइस कहते हैं, दैट सब्लाइम्स एट 193 Kelvin and of that sublimation of substrate that is of 25.2 kilojoule mole inverse. Naphthalene sublimates slowly and for this the sublimation is 73.0 that is kg mole inverse. Naphthalene भी sublimize होता है बट वो थोड़ा स्लोली होता है, इस वजह से 73.0 किलोजूल मोल इनवर्स है। नाउ स्टैंडर्ड एंथैल्पी किसकी बात करते हैं इन टर्म्स ऑफ स्टैंडर्ड एंथैल्पी हियर। So standard enthalpy of the sublimation that is of delta a subscript is the change in the enthalpy when 1 mole of the solid substance sublimates at a constant temperature and under the standard pressure of 1 bar. In the reference to this, we can say that the magnitude of the enthalpy that change depends on the strength of that intermolecular interaction of the substance undergoing to the phase transformation. For example, the strong hydrogen bonds between the water molecules holds them tightly into a liquid phase. And for an organic liquid की अगर हम बात करते हैं, organic liquid में such as acetone हम ले सकते हैं in the terms in the case of organic liquid की अगर हम बात करते हैं, organic liquid में हमारा जो है that is terms of acetone here, the intermolecular dipole interactions are significantly weaker. Thus, it requires the less heat of the vapors of 1 mole of acetone than that it does not vaporize 1 mole of water as well. That we will discuss this in the following table, that the values of the standard enthalpy change, fusion and the vaporization for some substances that is represented here. This is a table that where we are discussing the standard enthalpy change of the fusion of the vaporization here. So these were the table, these are the table that is your substance has been represented here, and that is TF by Kelvin, that is of temperature of fusion of Kelvin, change of fusion of enthalpy, and that is of mole inverse, and that is temperature here, and with reference to the vaporization that is represented here. So for the N2, this is 63.15, this is 6.72, and 77.35 and 5.59. NH3 के लिए हम बात करते हैं 195.40, 5.65, 239.73 and 33.35. In terms of H2O, 273.17, 15, 6.01, that is 372 Kelvin and 40.79. For HCl, 159.0, 1.99, 992, that is, and 188.0 here, and then 16.15 here. Now for the terms of the NaCl here, NaCl के लिए 1081.0 and 28.8 and 1665.0 and 170.0. CO कार्बन मोनोऑक्साइड के बारे में बात करते हैं, that is 68.0 here, 6.836, that is 6.836, 82.0 and 6.01 here. Where we're talking about C6H6, and that is 278.65, 9.83, 353.25 and 30.8 here. CH3CO CH3, in terms of that we have 177.8, 5.72, 329.4 and 29.1. CCl4 के केस में हम बात करते हैं तो 250.16, 2.5 and 349.69 and 30.0 here. These were the standard enthalpies, that is change of fusion of the and vaporization here. In terms of this, now we'll discuss numerical related to this topic, that what we had discussed here is here, that is T of F and T of B are melting and boiling point. This is your melting point and this is your boiling point respectively. So here we have a question here, that is a swimmer coming out from a pool is covered with a film of water weighing about 18 gram. Basically एक swimmer है वो pool से निकला है, उसके ऊपर एक फिल्म बनी हुई है, फिल्म वो मूवी वाली फिल्म नहीं, एक फिल्म इस तरह की, लाइक पतली सी लेयर जो जिसे कहते हैं पानी की, जो कि आपका 18 ग्राम की है। हाउ मच हीट मस्ट बी सप्लाई टू इवेपोरेट दिस वाटर, कितनी हीट चाहिए कि ये 18 ग्राम ऑफ जो फिल्म बनी हुई है ये इवेपोरेट हो जाए, हट जाए एट 298 केल्विन। कैलकुलेट द इंटरनल एनर्जी ऑफ द वेपराइजेशन एट 100 डिग्री सेल्सियस। आपको इंटरनल एनर्जी ऑफ वेपराइजेशन को कैलकुलेट करना है एट द 100 डिग्री सेल्सियस, which delta vaporization for the water and at it is 373 Kelvin, that is equals to 40.66 kilojoule mole inverse. Now we will go through the solution here. So the solution we had, we can represent the process of evaporation as in the form of 18 gram of H2O, that is in the presence of the. So here we can represent the process of evaporation, that is 18 gram of H2O, that is in the form of liquid, and that is vaporization has been gone through, and that 18 gram of H2O मिलेगा, that is in the form of the gases here. Vaporization के बाद number of moles in 18 gram of H2O liquid is 18 upon 18 mole inverse, that is equals to 18 ones 18, 18 ones 18, that is of 1 mole here. Number of moles हमें कितने मिलेंगे, 1 mole, and that change in the vaporization U, that is delta of vaporization H, that is of subscript here, and that is minus P, where the vaporization, that is of delta minus P of delta V, that is equals to delta of vaporization minus delta of Ng RT here. Consuming the steam behaving as an ideal gases here, that is the change in vaporization, and delta that is NGRT, and that is equals to 40.66 kilojoule mole inverse minus, that is of 1, and then 8.31 of 43 Kelvin inverse mole inverse, that is 373 K, and that is 10 to the power 3 kilojoule, that is then Kelvin here. This is the values that has been represented here, that in the form of the question that what they had given you. When we are solving this 40.66 minus 33.10, then we'll get 37.56 kilojoule mole inverse, that is the change in vaporization that we will get here. Okay, and now moving ahead with reference to this only, and that what we have to discuss here is the standard enthalpy of formation. Standard enthalpy of formation क्या होता है? The standard enthalpy change for the formation of 1 mole of a compound from its element in their most stable states of aggregation, also known as reference state. So basically जो आपका standard enthalpy change देखने को मिलता है हमें for the formation of 1 mole of a compound that from its element to its most stable, if I'm talking about more stable states for the aggregation, that is also known as, इसको हम reference state भी बोलते हैं, and this called standard molar enthalpy. उसे हम standard molar enthalpy भी बोलते हैं. Enthalpy of the formation, that is the symbol that has been represented by the delta FH of F subscript here. Okay, in terms of this, where the subscript, this F which is represented here, that indicates that 1 mole of the compound in the equation has been formed in that state, standard state from its element and in their most stable of the states of aggregation. This references state of an element as its most stable state of the aggregation at the 25 degrees Celsius at 1 bar pressure. And for example, we can see the reference that state of the dihydrogen, and that's H2 gas, or those of dihydrogen will take gas, and the carbon and the sulfur, that is O2, we can say that, and graphite would be in the form of the graphite, carbon would be in the form of the graphite, and that the sulfur is in the form of that is in the form of reactions. Some reactions were the standard molar enthalpies formation that had been taken given here, and now we'll discuss those equation here with reference to this. So before discussing those equation, we'll discuss this one. This is a table that is a standard molar enthalpies of that particular formations, that is of delta of E, that is of H bar, that at the 298 Kelvin at for the few selective substances that has been taken here. These were the representing the substances, and that's the delta R of H per kilojoule mole, and that is your substances, and that's the same. So for the Al2O3, that is in the form of solid state, and it is minus 1675.7. This is the substance that is Hi in the form of gas, state is gas, and that is plus 26.48. The second will be BaCO3, that is in the form of solid, and that is minus 1216.3, and this is KCl, that is state is solid, and that is minus 436.75. Br2, that is in liquid state, and that is 0, and KBr, that is in solid state, that is minus 393.8. Br2, that is in the form of gas, लिक्विड स्टेट में था तो जीरो था, बट गैस फॉर्म में है तो that is plus 30.91. MgO, that is in solid form, and that is minus 601.70 here. Now with a reference to CaCO3, that is in the form of solid, that is minus 1206.92, and Mg, that is OH whole twice, that is of solid state, that is minus 924,924.54. Where terms of carbon की बात करते हैं तो डायमंड के रेफरेंस में that the change is plus 1.89, and NaF that is in the form of the state solid, and that is minus 573.65. Where the carbon that is in the form of graphite, the change is 0, and NaCl, that is in the form of solid, that is 411.15. CaO, that is in the form of here, that is in the form of solid here, and that is minus 635.09. NaBr, that is in the form of solid, and that is we have is minus 361.06. CH4, that is in the form of gases here, and that is minus 74.81. And NaI, that is in the form of solid, and that we have is minus 287.78. C2H4, that is in the form of gases here, and that we have 52.26, and that NH3, that is in the form of the gases, that we have minus 46.11. CH3OH, that is in the form of liquid, we have a minus 233.86, and NO, that is in the form of gases, that we have is plus 90.25. Where we have C2H5OH, that is in the form of the liquid here, that is minus 277.69, and where NO2, that is in the form of gases here, this is NO and this is NO2, and that is plus 33.18 here. Now moving ahead, we have another one, and that will be your C6H2, that is in the form of the liquid here, and that is plus 49.0, and then PCl3, that is in the form of liquid, and that we have is minus 319.70. Carbon monoxide, that is gas, and that is minus 110.53, and PCl5 in solid form, that is minus 443.5. Carbon dioxide, that is CO2, that is in the form of the gases form, and that is having a minus 393.51, and SiO2, that is in the form of solid, and that we have minus 910.54. Now moving ahead, we have C2H6 in the form of gas, we have minus 84.68, and that is SnCl2. We have it is in the form of solid, and that is minus 325.1 here. Cl2, that is in the form of gas, that we have is 0, and Cl4, this is SnCl4 here, as this is SnCl2, that is in the form of liquid, we have minus 511.3. Now C3H8 that we have in the form of gas here, and that is minus 103.85, and SO2, that is in the form of gas, we have minus 296.83. In the form of N, that is C4H10, that is in the form of gas here, and that is minus 126.15, and SO3, that is in the form of gas, that is minus 395.72. HGS, that is in the form of solid, that is in red in color, and that is minus 558.2. SiH4, that is in the form of gas, and that is plus 34. H2, that is in the form of gas, that is 0, and SiCl4, that is in the form of gas, that is minus 657.0. H2O, that is in the form of gas here, and that is minus 241.82, and carbon, that is in the form of gas, that is plus 716.68. H2O, that is in the form of liquid, या gases में या liquid में है, that is minus 285.83, and hydrogen, that is in the form of gas, that is 200 plus 217.97, where HF, that is in the form of gas here, and that is minus 271.1 here, and then chlorine, that is in the form of gas, that is plus 121.68. HCl, that is in the form of gases here, minus 22.31 here, and Fe2O3, that is in the form of solid, that is minus 824.2 here. HBr की reference में बात करते हैं, that is in the form of gases here, minus 36.40 here. and with reference to that, this is the standard molar in these were the in standard molar enthalpies of the formulas, that is delta F of H subscript at the 298 Kelvin, and of a few selected substances that we had discussed here. Now with reference to that, we'll discuss some of the equation. Here this is your H2, that is in the form of gas, plus half of O2, and that is of in the form of gas, that form H2O, that is in the form of liquid here. Where delta F, that is of H subscript here in the form, and that is equals to minus 285.8 kilojoule mole inverse. Where the C, that is a graphite, that is in the form of solid, and plus 2 H2, that is in the form of the gas, and that is CH4, that is in the form of the gases here. With reference to that, delta F of H is a subscript, that is equals to minus 74.81 kilojoule mole inverse, and where 2 carbon, that is of graphite, and that we have in the form of solid here, plus 3 H2, that is of gram, and plus half of H2O, O2 gas, and that is C2H5OH, that is in the form of the liquid here. Where delta F of fusion of H F subscript is minus 277.7 kilojoule mole inverse here. In terms of while thinking about this, it is important to understand that the standard molar enthalpy of that formation, that is of delta F, or where we are talking about delta F H subscript, is just a special case of delta R H subscript, where 1 mole of the compound is formed from its constituent element, as it in the above three that we had discussed, where 1 mole of each water, methane, and ethanol is formed. In contrast to that enthalpy change for an exothermic reaction, we have another reaction, that is this COO, that is in the form of solid, plus CO2, that is in the form of gas, and that is CaCO2, CaCO3, that they form calcium carbonate, that is in the form of solid air. That the delta FOH of subscript equals to minus 178.3 kilojoule mole inverse. This is the reaction, that is exothermic reaction, that what we can see that. Okay, exothermic reaction here. Okay, with reference to that, that is not like I'm talking about this reaction, so we cannot say that is not enthalpy of the formation of calcium carbonate, where since the calcium carbonate has been formed from the other compound and not from its constituent elements here. Also, for those reaction given below, that the enthalpy that we had the standard enthalpy of the formation, that of delta R of H as substrate for the HBr, we'll take HBr here also, and that is H2O here in the form of the gases, and that is combined with Br2, that is in the form of liquid, and that combined in form that is in the form of gas, and that is from 2HBr. For here, the delta R of HF subscript is minus 72.8 kilojoule mole inverse, and here for 2 moles of, instead of 1 mole of product is formed from the element, that we can say that delta R of H equals to that we have 2 delta F and then H of subscript here. Okay, with reference to when I'm talking about the HBr here. Here, therefore, by dividing all the coefficients in the balanced equation, and then these were the expression that has been formed in terms while we are talking about the equation. So now we will do further more about these equation, and that we will discussed here, and the enthalpy of that formation, that to be in terms of HBr, that is in the gas state, that could be represented by the half of H2 gas and plus half of Br, then in the liquid state, and that form the HBr in the gas state, where the delta FOH subscript equals to minus 36.4 kilojoule mole inverse here. Okay, with reference to this standard enthalpies of formation of some common substances, while by converging the standards enthalpies for the formation, that is of delta R of H of an element or in the reference to state, and that is it must stable, the state of the aggregation is taken is as 0. And suppose you can you are a chemical engineer and want to know how much heat is required to decompose the calcium carbonate to lime and carbon dioxide. So with all that substance in their standard state, we will just say that the calcium carbonate in the solid state, and that react here and then form the calcium CaO and the solid state, and CO2 in the gaseous state, and that delta R of H, that enthalpy don't know. with reference to that, here we can make a use of the standard enthalpies of the formation and the calculator of that enthalpy that can change for that particular reaction. That the following general equation can be used for the enthalpy, that is the change in the calculation. We can use the general enthalpy general equation, that is of delta R H F subscript is sigma of I A of I delta F of H subscript of product, and where sigma minus and sigma of I B of I and delta F of H subscript of reactant. These were the coefficients of stoichiometry for product, and this is of reactant here. This is the sigma that is representing the summation here. This is the actual reaction equation that what will form it out, and this is the how from this equation you can find it out all the reaction enthalpies here. Okay, so where in terms of this, as I told you, where A and B are representing the coefficient of the product and the reactant of the balanced equation, let us apply all the above equation, that decomposition of the calcium carbonate here. The coefficients of A and B at 1, and take it out in the form of जो भी calcium carbonate वाली हमने equation पढ़ी उसी को हम एक बार निकाल के देखते हैं. Let go through delta R H subscript equals to delta F of H plus, that is Ca. तो that S, क्योंकि प्रोडक्ट पहले लेते हैं तो हमारे पास प्रोडक्ट ये बन रहा है CaO, CaO ये वाला and this then we'll take the reactant here. COS in the state plus, then delta F of H, then a CO2 that is in the form of gas, then minus, because minus if delta F of H F subscript, then CaCO3, and that is in the form of the solid here. Okay, so here this will be the one, that is minus 635.1 kilojoule mole inverse. अभी मैंने टेबल आपको बताया था, उसमें मैंने सारी चीज़ें आपको बताई हैं, ऑलमोस्ट बहुत सारी चीज़ें कवर अप ऑलरेडी कर ली है, तो उसमें आपको वहाँ पे ये मिल जाएगा माइनस 635.1 किलो जूल मोल इनवर्स प्लस एंड देन 1, that is minus 393.5 किलो जूल मोल इनवर्स, and that is minus 1, and that minus 12.06.9 kilojoule mole inverse. इसको further हम solve करेंगे, this will be multiplied and that's the same here, so we'll just do that. इनको plus करके फिर हम इसको minus करेंगे, we'll get 178.3 kilojoule mole inverse here. Okay, so thus we can say that in terms of this, that thus the decomposition of CaCO3 in the solid state is an endothermic process, and you have to heat it up for getting the desired product. You can just find it out after solving this. Now moving ahead, we have a D1, that is thermochemical equation, that we'll discuss, and in terms of that we'll discuss some of the necessary conditions also, and the conventions regarding the chemical equation, and then we'll discuss the Hess law of the constant heat of summation, and then after that we'll end up this session, and then we'll discuss in the next topic, and that we have here is